So yesterday we are in the functional isomers. Actually we have discussed already CnH2n plus 2O is the general formula for alcohols and ethers. That's why alcohols and ethers are functional isomers. Yesterday we have already given this example. Ethyl alcohol and dimethyl ether. These two are functional isomers. So this is the first example for functional isomerism. Second example, aldehydes and ketones. Aldehydes and ketones with the same molecular formula. Same molecular formula. Represent functional isomers. For example, you can take CnH2nO. The CnH2nO, if you write if n is equal to 3, if n is equal to 3, then you can write in two ways. Okay, n is equal to 3 means the formula becomes C3H6O. Now the C3H6O can be represented in two ways. CH3, COCH3, which is called a propanone. Propanone is IUPAC name. The common name is acetone, which is used as a nail polish remover. One of the most common use of acetone is a solvent actually. It is used as a nail polish remover. So now the other way of representing CH3, CH2, CH double bond. This is propanol. So one is ketone, propanol is a ketone, propanol is an aldehyde. So they represent a pair of functional isomers. What is the first example we have given? Alcohol and ether. If they have same molecular formula, they represent a pair of functional isomers. What is the second pair we are giving? Aldehyde and ketones. They also represent a pair of functional isomers. You know, aldehydes react with the Tollens reagent, forming silver mirror, a white precipitate of silver coated on the inner walls of the glass tube. So aldehydes give silver mirror test. Ketones do not. Similarly, aldehydes when react with Fehling's reagent, which is ammonical cupric sulfate, stabilized by a tartrate, they give red precipitate. Ketones do not. Similarly, aldehydes react with Bendix and give red precipitate. Ketones do not. Like that, isomers always have same molecular formula but different properties. Third example we can give. Carboxylic acids and esters are functional isomers if they have same molecular formula, provided they have the same molecular formula, MF. For example, CnH2nO2. Actually, this is the general formula for both carboxylic acids and esters. CnH2nO2. If n is equal to 2 or n is equal to 3, C3H6O2. Now the C3H6O2 can be written as CH3, CH2, COOH. See, there are 3 carbons, 6 hydrogens and 2 oxygens. It is called a propanoic acid. Propanoic acid. Last student, you are doing biology, I think. Some students do like that. Chemistry class they study biology, biology class they study physics, like that. Finally they will gain nothing. So the next one, CH3 COOCH3. Whenever COO group is there, it is called ester. Its common name is methyl acetate. This is methyl group, this is acetate ion. What is the common name of this ester? Methyl acetate. In IUPAC, methyl ethanoate. So propanoic acid and methyl ethanoate represent what kind of isomerism? Functional group isomerism, because here the functional group is COOH, here the functional group is COO. That's why their properties differ COOH shows the most common property. It will give quick effervescence with sodium bicarbonate. If we add some sodium bicarbonate, COOH group will give carbon dioxide with full of bubbles, but ester won't give. And carboxylic acids have different smell. Esters have pleasant fruity odors. Most of the fruity flavors, the ice creams which you are eating, are added with artificial esters. So vanilla ice cream really do not contain vanilla extracted from the plant. Some essence is added. So flavoring agents. Esters are flavoring agents. So carboxylic acids and esters. The fourth example I am going. Cyanides and isocyanides. Cyanides and isocyanides also represent a pair of functional isomers. Cyanide means RC triple bond N. And isocyanide RN triple bond C, where N is plus, C is minus. If you want to write ethyl cyanide, ethyl cyanide, common name. What is that IUPAC name? Cyanides in IUPAC are called as cyanides in IUPAC are called as alkane nitriles. Alkane nitriles. So its IUPAC name, propane nitrile. And CH3, CH2, N triple bond C. It is ethyl isocyanide. Ethyl isocyanide. Common name. What is the IUPAC name? IUPAC name of ethyl isocyanide. Right? Ethyl carbylamine. Isocyanides in IUPAC system are called as carbylamines. Now the fifth example. So ethyl cyanide and ethyl isocyanide. This common name is ethyl cyanide. This common name is ethyl isocyanide. They represent what? A pair of functional isomers. You are back. What is your name? Spelling? Swanky. Okay. So Swanky asked the same doubt yesterday. So he brought a question in which ethyl chloride is treated with AgCl. Compound X is formed. The functional isomer of X. They ask not X. The functional isomer of X So actually with AgCN, when alkyl halides react with AgCN, the major product will be ethyl isocyanide. You will get this is the main product. X is this. But they have not asked X. The functional isomer of X is this. Hope now you might have followed this. So that's why I recollected your doubt, which is relevant here. Now, fifth example, alkynes and alkadienes. Alkynes and alkadienes. Represent functional isomerism. Example, the general formula of alkyne CnH2n minus 2. You all know. With this, you can write if n is equal to 4. If n is equal to 4. C4H6. C4H6, which I can write CH3, CH2, C triple bond CH. I can also write CH3, C triple bond, C triple bond, triple bond C, CH3. In two ways I can write. The same thing I can write CH2 double bond CH, single bond CH, double bond CH. So both are C4H6. The first one is 1-butene. The second one is 2-butene. Here it is 1,3-butadiene. Suppose if I give numbering like this and ask you the questions like this, what is the isomerism exhibited by 1 and 2? You have to say position isomerism. They differ in the position of triple bond. They have same molecular formula, but they differ in what? Position of triple bond. So 1 and 2 represent position isomers. 1 and 3 or 2 and 3 represent functional isomers. Because triple bond is the functional group in alkynes, double bond is the functional group in alkenes. So they differ in the nature of functional group. That's why 1,3 or 2,3 represent what? Functional isomerism. 1 and 2 represent what? Position isomerism. Between 1 and 2, which will react with sodium metal and liberate hydrogen? So the answer is 1, because it has acidic hydrogen. The hydrogen linked to sp hybridized carbon is called acidic hydrogen. Acidic hydrogen. That's why if 1 and 2, if you want to distinguish which is 1-butene, which is 2-butene, you add some sodium metal. 1-butene will liberate hydrogen because it has acidic hydrogen. 2-butene has no hydrogens directly attached to triple bonded carbon. Hydrogens are attached to sp3 carbons there. Here these two carbons are sp3 carbons. Triply bonded carbons are sp carbons. So what is acidic hydrogen? The hydrogen that is directly linked to triply bonded carbon or sp carbon. They show particular properties, like one property just now I discussed. They liberate hydrogen with sodium metal. They react with soda amide and liberate ammonia. They react with the Tollens reagent and form a white precipitate of silver compound, silver alkyanide. They react with ammonical cuprous chloride, forming a red precipitate of copper alkyanide. So write all those points now itself. Alkynes containing acidic hydrogen. Alkynes containing acidic hydrogen within brackets, H atom directly attached to triply bonded carbon or sp carbon. H atom attached to directly attached to triply bonded carbon or sp carbon, bracket close. Show the following characteristic properties. Show the following characteristic properties. Number 1, liberate hydrogen with sodium metal. Number 1, liberate sodium metal with liberate hydrogen with sodium metal. Number 2, liberate ammonia. Liberate ammonia with soda amide, NaNH2. Liberate ammonia, NH3, with what compound? NaNH2. What is the name of NaNH2? Soda amide. SODAMIDE. Soda amide. Number 3, react with ammonical silver nitrate. React with ammonical silver nitrate within brackets Tollens reagent. Within brackets Tollens reagent and form a white precipitate of silver alkyanide, AlKyNide. White precipitate of silver alkyanide, AlKyNide. Silver alkyanide. The last property, react with ammonical cuprous chloride. React with ammonical cuprous chloride, forming a red precipitate of copper alkyanide. I think in one of your papers I have seen, they have given these three compounds. CH triple bond CH, one compound. CH3C triple bond CH is another compound. CH2 double bond CH2 is another compound. Decreasing order of acidic strength. Decreasing order of acidic strength. Decreasing order of acidic strength. So the answer is 1 greater than, 2 greater than 3. Why 1 is greater than 2? Here the number of acidic hydrogens are 2. 2 hydrogens are directly linked to triply bonded carbon. Here only 1 acidic hydrogen. That is one reason. Second reason, if the first one loses a proton, 1H plus, the resulting alkyl ion is not destabilized, but whereas if propyne loses acidic hydrogen, the resulting alkyanide is unstable because methyl group is plus I group, electron releasing. It is electron pushing. When it pushes electrons, more negative charge will be accumulated on the carbon. If somebody pushes electrons, the negative charge will be more accumulated. Charge accumulation is always a destabilizing factor. Charge dispersal is always a stabilizing factor. So there are 2 reasons why 1 is more acidic than 2. 1 has more number of acidic hydrogens. Number 2, if 1 loses a proton, the anion is not destabilized. If the second compound loses a proton, the anion is destabilized by plus I effect of the methyl group. The plus I effect of methyl group. Now coming back in the functional isomerism, the last part, primary, secondary, tertiary amines having the same molecular formula represent functional isomerism. This represents functional isomerism. Example, C3H9N, that is CN He3N N. If N is equal to 3, C3H9N. Now the C3H9N I can write in 3 different forms. One I write CH3, CH2, CH2NH2. Whenever there is propanamine is the IUPAC name, common name is propylamine. The next one, CH3, CH2, NHCH3. It is a secondary amine. Secondary amines are having the functional group NH. Primary amines are having the functional group NH2. So it is N-methyl ethanamine. This is IUPAC name. N-methyl, N is having the methyl group. This part is ethanamine. So N-methyl ethanamine. Common name ethyl methylamine. What is the common name? Ethyl methylamine. The third one, what I write is CH3N tri-CH3. It is a tertiary amine. Now its common name is trimethylamine. Trimethylamine. IUPAC N, dimethyl, NN dimethyl methanamine. Two methyl groups are present. NN dimethyl. This part is methanamine. So here N is that functional group. So in what aspect they differ? Though they have the same molecular formula, C3H9N, all have the same molecular formula. But in what aspect they differ? They differ in the nature of functional group. What is the functional group in primary amines? NH2. What is the functional group in secondary amines? NH. What is the functional group in tertiary amines? N. That's why primary amines are identified with carbylamine test. So whenever a mixture of amines are there, if you want to only identify primary amine, you have to add chloroform plus KOH. Immediately an intolerable smell or offensive smell is noticed due to the formation of an isocyanide. So that indicates there is NH2 group. So primary amines are best identified by which test? Carbylamine test. They react with chloroform and KOH, forming isocyanides which are having intolerable or offensive smell, which you can't tolerate. Now look at the next isomerism, that is metamerism. Metamerism. So compounds with the same molecular formula, but different properties. Due to different alkyl groups attached to the same functional group. Example, ethers, number 2, secondary amines, number 3, esters, number 4, anhydrides. So all these will exhibit metamerism. Now first we take up ethers. Ethers can be written as, we take ethers as an example, like C4H10O. If you are asked to write the metamers, you can write 3 metamers here. C2H5OC2H5, diethyl ether. Or the second one you can write CH3OCH2 CH2CH3. This is methyl N-propyl ether. The last metamer CH3O CH3 twice, methyl isopropyl ether. What these 3? First one is diethyl ether. What is the second one? Methyl N-propyl ether. What is the last one? Methyl isopropyl ether. All these 3 are having same molecular formula. What is that? C4H10O. In what aspect they differ? They differ in terms of nature of alkyl groups. That's why they are called as metamers. These 3 are metamers. Similarly, if you want to write secondary amines, RNHR and RNH, some R dash. If you want to write esters, RCOOR and RCOO, R dash. If you want to write anhydrides, RCOO, COR and RCOO, COR dash. R can be any alkyl group. So how to represent the metamers of secondary amines? They can be in the form of RNHR or RNHR dash. R and R dash are different. Like that. The next one, tautomerism.
We've done it yesterday, so I would have done it.
Achha, tautomerism already completed.
No, sir.
Tautomerism. So what is your name?
Lanyo Kupang.
Very difficult. Last 3 letters. Pang. P-A?
P-A-N-G.
Dr. Pang. So she will explain tautomerism. Can you explain? No, you can't. Acha, here the dong, pong, these are common suffixes. Even I am going to purchase some lakadong turmeric, India famous. So this lakadong turmeric contain curcumin, an alkaloid present in that, in highest percentage. But many online agencies are showing that we sell pure form, but usually turmeric is contaminated with lead. Lead compounds are yellow in color. They add some lead compounds to give that bright yellow color. So we have to purchase from authentic sources. Okay. Tautomerism, a special type of functional isomerism. So in tautomerism, there is an internal rearrangement. Internal rearrangement of a pi bond and migration of an alpha hydrogen present on saturated carbon, that is sp3 hybridized. sp3 hybridized carbon. For example, I will show a compound like this. Actually, this is called a keto form. In keto form, the carbon adjacent to carbonyl group C double bond O is called alpha carbon. This is alpha carbon. So condition, whenever a keto has to be converted into enol, what is the prior condition? There must be at least one alpha carbon which must be saturated, that is all single bonds, that is sp3 carbon. This carbon is sp3 carbon. So whenever Whenever you want to write or convert a keto form into enol form, the must condition is the keto form should contain an alpha carbon which must be saturated, that is single bonded, or it is sp3 hybridized carbon. Only in such case the pi bond will shift to more electronegative oxygen. Pi bond will shift to more electronegative oxygen. So one of the alpha hydrogen give its bond between carbon and carbon. Its bond is shifted between carbon and carbon. This H plus will migrate to O. So when all these occur, the resulting structure if you want to write, this O become single bond O and H is migrated to this OH. This is not disturbed. This pi bond is not disturbed. Here this bond become double bond because the CH bond shifted here. You will get phenol. Phenol is enolic form. Enol form. This is keto form of phenol. See, actually in the equilibrium, when I write a double arrow in the equilibrium expression, please look at, I wrote a big arrow towards enol and a very small arrow towards enol, which is quite a contradictory thing. Usually keto forms are more stable, enol forms are less stable. But here enol form is more stable and it is almost more than 99%. It is less than 1%. Write a point here. Later that we will write a question. Or write a question, assertion. Usually keto form is more stable. Assertion. A. Usually keto form is more stable than enol form. Usually keto form is more stable than enol form, but in phenol, the enol form is more than 99%, is greater than 99%, and its keto form is less than 1%. And its keto form is less than 1%. That is, the assertion is over. Reason. The enol form of phenol contain 3 alternate pi bonds. The enol form of phenol contains 3 alternate pi bonds. That is a conjugated system. And will have resonance stability. So here, if you observe both, so the answer is both are true. Why phenol is enolic form, it is more stable? Because the ring contains 3 alternate pi bonds. Whenever alternate pi bonds are there in organic chemistry, we call it as a conjugated system. Conjugated systems are more stable due to resonance. Because it is more stable, the equilibrium is moving more towards the enolic form and very less towards the keto form. Write the next point in the same heading. Write the tautomers of acetone. So this is acetone. Is acetone is a keto form or enol form? It is a keto form. What is the necessary condition when a keto form want to convert into enol form? It should have alpha hydrogens which are linked to saturated carbon, that is sp3 carbons. Here 2 sp3 carbons are there, which is alpha carbon here. This is also alpha carbon. This is also sp3. 6 alpha H are there. At least 1 alpha H is enough to exhibit tautomerism. So what is the rearrangement that is going to happen? The C double bond O, pi bond shift towards oxygen. One of the CH bond shift between C and C. H plus will migrate to O minus. So this is called tautomerism. So here we write a small arrow towards enol form, a big arrow towards keto form. Because usually which form is more stable? Keto form is more stable. So the resulting compound is CH3, COH, double bond CH2. This is enol. Write an important note. The number of sigma and pi bonds in keto and enol forms are the same. The number of sigma and pi bonds in both keto and enolic forms is the same. Because this note is required in one competitive exam. They ask the number of sigma and pi bonds in the enolic form of acetone. They asked. So you need not waste time to convert acetone into its enol form and count sigma and pi bonds. Directly take acetone. How many sigma bonds are there? 9 sigma are there. 9 sigma and 1 pi. Write sigma, this is sigma, this is sigma, this is sigma. Like that, if you write sigma, 9 sigma and 1 pi. Here also if you count, you will get 9 sigma, 1 pi. So number of sigma and pi bonds in both of them are same. The next point is why the keto form is more stable than enol form? Answer: the C double bond O has greater bond energy than C double bond C. So the reason for keto form more stable than enol form, the reason for the keto form is more stable than enol form is that in keto form the C double bond O is that in the keto form the C double bond O has greater bond energy than the C double bond C of the enol form. How many of them will exhibit or will show keto-enol tautomerism? So first one I am giving like this. One. This is the second one. Third one. How many of them will show keto-enol tautomerism? So Dr. What is his name? Ricky Ponting. Dr. Ricky Ponting. And another doctor. Dr. Dong. Tommy Hillflyer. Okay. Tommy. So Dr. Tommy is saying only 2. Dr. Ricky is saying 3. Dr. Tommy is correct. 1 and 2 are correct. Third won't exhibit. Because there is no this alpha carbon, 2 alpha carbons are sp2 hybridized. This is also sp2. Here this alpha carbon is sp3. Here one more alpha carbon, sp3. This is also alpha. Double bond adjacent carbon is C double bond O adjacent carbon is alpha. Here this is alpha carbon which is sp3. Compounds like acetyl acetone will have more percentage of enol, due to the formation of intramolecular hydrogen bonding. Due to the formation of intramolecular Actually, this is acetyl group. CH3CO group is called acetyl group. This part is acetone. Acetyl acetone. Total how many alpha hydrogens are there? 8, correct. 3 on the terminal carbon, this 3 alpha hydrogens in the terminal, 6 in the middle, 2, total 8. 8 alpha hydrogens are there. So enolizable. But if you write one of the tautomeric forms, this pi bond will shift in tautomerism. Whenever a keto form is to convert into enol form, the C double bond O, one of the pi bonds should shift towards oxygen. Immediately one of the alpha hydrogen should give its bond pair to between C and C. H should be migrated to oxygen to become OH. So this is what we are doing. So if you write this CH3, it becomes COH double bond CH, C double bond O, CH3. Now this OH group contains H as partial positive, O as partial negative. Here double bond O also O contain partial negative charge. So this partial positive H, partial negative O develop a weak electrostatic force which is called hydrogen bonding. Whenever hydrogen bonding is formed between two groups of the same molecule, we call intramolecular hydrogen bonding. Because of this intramolecular hydrogen bonding, a ring is formed. Chelation. Chelation means ring formation that increases the stability. That's why here percentage of enol is more. Whenever there is a possibility of intramolecular hydrogen bonding, the enol content will be more. Usually which is more? Keto form. Because C double bond O is stronger than C double bond C. So this is all about tautomerism. Now we have completed the structural part of the isomerism, that is position, chain position, functional, metamerism, tautomerism. 5 types. Write the next heading, stereo or space isomerism. Stereo or space isomerism. Generally students feel difficulty here because you have to imagine the molecule in a 3D space. You require more imagination. Or actually to understand stereochemistry in a more detailed way, we should have the models, 3D models. Actually I forgot to bring. I have one set of ball and stick models. We call it as ball and stick models. Easily we can construct the model and see 3-dimensional arrangements. So in the stereo or space isomerism, which we divided into 2 types, conformational and configurational. Write the first heading, conformational isomerism. Conformational isomerism. CONFOR. conformational isomerism. It arises due to the free rotation of carbon-carbon, single bond. Full stop. The free rotation of C dash C, carbon single bonds carbon, in alkanes require require 3 kilocalorie per mole of energy. Which is very much supplied by the room temperature. Which is very much supplied by the room temperature. Which is supplied very much by the room temperature. Hence, at room temperature, conformers are go on interconverting. And it is very difficult to separate them. So, for example, if you take the example of ethane, the molecule is viewed along sidewise, or even I can write a better way. So the observer is observing the ethane C2H6 from a slanting way. So actually the front carbon, this is the front carbon where observer is directly viewing this carbon. This carbon is a rare carbon or behind the carbon. So there are two carbons, one in the front, the other is behind, connected by a single bond. Front carbon has 3 hydrogens, back carbon is also having 3 hydrogens. If you rotate this, the hydrogens also change their positions, position in the space. Initially let us assume that one hydrogen is behind the other hydrogen. What I wrote there. This H is behind this H. This H and this H are one behind the other. So if one atom is behind the other atom, so observer cannot see the H atom behind the front hydrogen. That's why we call it as eclipsed form. So in conformers, eclipsed conformer is one of the type. If I slightly rotate 1 degree, you can see the second hydrogen also you can see. If I rotate 60 degrees, you can have a better view. So that is called a staggered form. So I write the staggered form also by rotating this carbon-carbon single bond. Single bond is rotated. This is eclipsed conformer. Conformer of ethane by 60 degrees rotation. Now I write this like this. So if I rotate this H will come down. Or I write even a better way. So this H will come down. So the observer is observing from here. You can see all the hydrogens. So this is called staggered form. Suppose if you do one more 60, again you will get eclipsed form. You may ask me why I have to rotate 60. I can rotate 1 degree or 2 degree or 10 degrees. Yes, you can have any degree of rotation. So this rotation of single bond will change the spatial arrangement of hydrogen atoms. If spatially one behind the other, this form is called eclipsed. If spatially they are not one behind the other, they are called staggered forms. But who will catch ethane molecule is not visible to your, or you can't catch the molecule. Wait, my dear ethane, I am holding it and I am rotating the single bond. Who will do that? We are not going to do that. That's why I gave one point there. The single bond rotation require how much energy? 3 kilocalorie per mole. And that is very much supplied by the room temperature. So at room temperature they are go on interconverting. Eclipse, staggered, different ways they are go on interconverting. That's why at room temperature you can't separate them.